So I welcome you all. Thanks for the numerous participation. I'm going to talk about the solid phase peptide synthesis in 384 well plates. In our establishment of the platform, we used the state-of-the-art parallel peptide synthesizer using 96 well plates to synthesize in one run a total amount of 384 peptides. If we want to move on to more challenging targets, we found that might not be enough. Current limitations in the peptide synthesis throughput are, of course, the microfilter titer plates, which are in the 96 well format. Somehow we were also surprised that there are basically no publications found for pursuing 384 well plate SPPS. But somehow in DNA synthesis, it was realized even in denser formats. And yeah, then we became curious, is that somehow possible? And for this, yeah, the aim was quite simple, like just increase the synthetic throughput by changing the well plate format from 96 to the denser one, 384. So in the first step, we just needed to make sure that we can find that we find a reactor which was commercially available. And this was the important factors were, of course, compatibility of the material, solvent retention, so that the reaction mixture doesn't just flow through. Of course, the well format, also that it is integratable into a state-of-the-art peptide synthesizer, and the well tips in terms of important for cross-contamination, but also for sealing purposes. So standard-wise, those microfilter plates are used. This one to the right hand side turned out to be sufficient good for our purposes. This one is our our synthesizer. Christian Ben already introduced the major parts, so I will be quite quickly go through. So we have syringe, we have a robotic arm for the XY axis, we have a manifold for washing, of course the 4 reactors in the 96 well format, building block, derivative rack, external and internal reservoirs. We had to develop new hardware for this, and we wanted to do as little as possible. So we focused only on the reactors, the multi-channel dispenser, as well as the derivative rack. This was done in collaboration with our in-house mechanical workshop, where then when we together prototyped, and they also fabricated then our ideas. So first we did. First, we focused on the reactors. On the picture, you see now the standard commercial configuration. On the right-hand side, the developed one. And the main difference here is basically that we included this adapter for the height compensation of the shorter 384 well plate to have the same height, so that we don't need to do any further changes. In the second step, we adapted the manifold from an 8-channel to a 16-channel, but not only this, we also increased the height so that we are not only capable to dispense accurately DMF, but also piperidine, which significantly shortens the synthesis time. With the commercial derivative rack, we can only fit 31 amino acids. In our fridge and collection, we have over 350 FMOC amino acids in hand, and we also want to integrate way more amino acids into our peptides. So this type of setup was not suitable for us. So what we did is then designed this plate here, fitting into the existing setup. What the main change here was that we just use deep well plates, 2, one as a reservoir holder, the other as a mixing deep well plate, either in 48, 96, or even 384 well deep well plate. Being now technically able to synthesize peptides in 384 microfilter plates, we struggled then to actually load the resin in so many wells. This practical issue and frustrating work we solved the following way. We have developed a size tester with 96 different dimensioned holes with a specific scale, and the resin swollen in its wet form will occupy a specific hole volume. These specific dimensions were then multiplexed into a array, and the 384 corresponding to the appropriate dimensions of the used microfilter plate. And the loading was then done the following way. So you have wet resin, you distribute it, you remove the excess, you then place the microfilter plate on top of it, you place it into the bucket, centrifuge bucket, you centrifuge 2 or 4 plates at a time, and within 5 to 10 minutes you can transfer all the resin uniformly into the plates. We then, of course, also synthesized peptides. So those are crude peptides released with the reductive release method. And overall, we were happy with the crude purity we obtained, sufficiently good for us to then afterwards further modify in even lower scale, like a nano or picomolar scale. So in summary, we could significantly increase the throughput, so 1,536 peptides per run. We can host way more building blocks now, which adds to the diversity of our libraries. And roughly one synthesis for 4 couplings takes about 36 hours for us. Overall, we have now synthesized more than 20,000 peptides, which we use as stock solutions, which are then subsequently further modified either at nano or picomolar scales to form many, many macrocycles. Here you then see actually our upgrade in action. To the left-hand side, the distribution of reagents from a deep well, 96 well deep well plate reservoir, and transfer the different liquids into the 384 well plate reactors, and then on the right hand side the 16-channel manifold, how it washes. Thank you very much for your attention, and I'm happy to answer questions if you have any before we continue to the case studies presented by Edward Will.